All right, well, after that excitement, let's get back to boring old math. So, simplifying rational expressions. A rational expression, as I started to write, is an algebraic expression that can be written as a quotient of two polynomials. And I'm sure that that totally clears it up for everybody, right?
Oh, yes.
Excellent. All right, so let's decode that a little bit because there's lots of words in there that we need to make sure we understand. So first of all, let's start with an expression. What is an expression? Yep.
An expression is a series of constants and variables linked with operators.
What kind of operators?
Linked with any mathematical operators that are not said to be equal to anything.
Okay? You're not wrong. Is that cleared up for everybody?
No.
Not really? Okay, so whoops, why does that always come up? An expression is simply I'm going to make it a little bit simpler. A sum or difference of one or more terms. So what do I mean by a term? So we have to keep breaking this down until we really understand it. So what is a term? Yeah?
Like, would like 2x squared be a term?
2x squared would be a term.
Like, just like x.
X would be a term.
Or 2, right? This is like a little piece of the expression.
Okay. So a term is a number, a variable, or the product of both. So for example, you could have a number like 3. You could have a variable x by itself. You could have 2x. You could have 6x squared. You could have 7x squared y cubed z to the 4th. Right? You can put as much of it together as you like. As long as they're all being multiplied together, that is one term. Okay? So an expression is a sum or difference of one or more terms. So an expression could be just a single term, or it could be 2 terms added together, or 5 terms added and subtracted. It can be as long or as complicated as it gets. Now, an expression and a polynomial are very similar, but before I get into that, what does the word algebraic expression mean? What piece does that add? When we started doing algebra, we introduced what into our math? Yep, variables. Because when we first started doing math, we just dealt with numbers. And when you were in elementary school, you started doing algebra. And the difference between working with just numbers and working in the area of algebra is that we start putting variables into our work. So we have letters that represent the values of unknown numbers. So an algebraic expression would have a variable in it somewhere, right? Because you could argue that 2 plus 5 is an expression. And it is. It's just not an algebraic expression. 2x plus 5, which has a variable in it, now it's an algebraic expression. That's the difference. Okay? So algebraic simply means there's variables in it. All right, now, polynomial. The definition of a polynomial and an expression are basically the same, but I want to add just a little piece to it. So a polynomial is a mathematical expression with one or more terms whose exponents are whole numbers and whose coefficients are real numbers. So this is an important distinction. So let's first of all look at examples of polynomials. Okay, so a polynomial can be as simple as 3x squared. We call that a monomial, right? Could be 2x plus 5. It could be x squared minus 7x plus 12. It could be 6x squared minus 4y squared, and so on. Those are all polynomials. Okay? Actually, just let's make this 4/3, because the coefficients can be real numbers, right? They can be decimals, they can be fractions, they can even be radicals, right? So the coefficients can have any value, any real number value, but the exponents have to be whole numbers. Okay? So by restricting the exponents to be whole numbers, that means that examples of non-polynomials would be something like, the square root of x plus 5. Okay, that's not a polynomial, because what would the exponent be for x if we wrote that as a power instead of as a radical? 1/2. 1/2 is not a whole number. Therefore, that has a exponent that's not a whole number. It's not a polynomial. Okay? Similarly, you couldn't have x as an exponent, because x it can have any value, which would include non-whole number values. Therefore, it would not be a polynomial. Similarly, you couldn't have something like this as a polynomial, because what would the power or the exponent be for x if we wrote that as power? This would be the same as x to the 1/2 plus 5. What would this be the same as? What makes x go down to the denominator? Pardon me? A negative exponent. So this would be 5x to the negative 1 plus 4. Negative 1 is not a whole number, right? So these are examples of non-polynomials. So none of our numerators or denominators are going to look like that. Okay, so it's important to know what a polynomial is, but it's also important to know what a polynomial is not. All right? All right, so we're almost through the definition. I'm just going to scroll back up here for a minute. So we know what an algebraic expression is. We know what a polynomial is. Now, what does it mean to write as a quotient of two polynomials? What does the word quotient mean? Everybody's heard about the word quotient before, right? You should remember this from elementary school. So what is it? Yeah? Not multiplication, no. Division. So the quotient is the answer you get when you divide two numbers. So if we're going to write something as a quotient of polynomials, that means write as a fraction. All right? So we're going to write it as a quotient of two polynomials. That means we're going to write it as a fraction where the numerator is a polynomial and the denominator is a polynomial. So here are some examples of rational expressions. So it can be as simple as a monomial numerator, monomial denominator. It could be something that looks like this. It could be something that looks like this. And so on. All right? Yes?
Could we have an integer alone in the denominator?
Yes, it could. Yeah, absolutely.
Alright, so whole numbers include 0.
Whole numbers include 0, yes. Whole numbers start at 0.
Okay.
Yeah. So you could have something like 4x squared over 5. That's still considered a rational expression. Even though 5 is not, doesn't have a variable in it, it's still considered a polynomial because remember I said a polynomial is a collection of terms. As long as there's a variable somewhere, numerator or denominator, it's still a rational expression. Okay? So, everybody with me so far? Okay. So, let's consider the rational expression (5 over 2x). Is a rational expression, agreed? It's got a monomial numerator, monomial denominator. Are there any values for x for which we would be in trouble? Right?
0.
Why?
You can't divide by 0.
So, if x equals 0, then this becomes 5 over 2 times 0, which would be 5 over 0, which is undefined. So when we're dealing with rational expressions where we have variables in the denominator, we have to be really careful that we don't allow the denominator to have a value of 0 because division by 0 is undefined. So if you think back to chapter 2 and we looked for restrictions on the variables and we looked for values of the variables for which it would make the radicand negative, and we said x can't be those values or x has to be the other values only. This is similar. Anytime we're dealing with a rational expression, one of the first things we have to do is look at the denominator and restrict the variable restrict it from being the values that would make the denominator 0. So let's, I'm going to write this down first. So since x equals 0 makes the denominator have a value of 0, we say that x equals 0 is a non-permissible value. Now, non-permissible value is a bit of a mouthful and a lot to write, so you'll see me abbreviate it NPV. Now, that's my abbreviation, that's not mathematical in any way. That's just me being lazy. So if you see NPV or you hear me say NPVs, that's what I mean, non-permissible values. So x is not permitted to be 0 because when x is 0, it makes the denominator 0, and when the denominator is 0, we're dividing by 0, which is undefined. Make sense? All right, so we're going to start by making sure that we can find and state all non-permissible values. So give the non-permissible values for the following rational expressions. All right, so this first one, x plus 3 all over 2x. What values for x would make the denominator equal to 0? Skylar? X equals 0. So we don't want x to be 0, so we write it this way. We say x cannot be equal to 0. Right? So we write non-permissible values by stating that the expression is only defined as long as x is not equal to 0. So when we were dealing in chapter 2, we gave all the values for which x could be so that the expression was defined. Now we're kind of doing the opposite, because there's only going to be a few numbers for which it's undefined. So we state what those few numbers are. Sometimes it's 1, sometimes it's more, depending on how complicated the denominator is. In chapter 2, we had a whole range of values for which we would say it's undefined. So we'd say x has to be greater than 0, for example. But here, we're saying x can be anything but 0. So we write it by stating what it can't be. So it's a little bit different than what we were doing before. Does it make sense? And everybody knows that that equal sign with a line through it means not equal to. Yes? You familiar with that terminology? All right, so let's try another one. What would the non-permissible value be here? Abby? 4. Everybody agree? Now, last block somebody asked me the first question, and I forgot to mention this. Do we have to say x cannot be equal to negative 3? So if somebody asked you that, how would you answer them? Justin?
X may be negative 3 because 0 over anything except 0 is defined.
Correct. So we can take 0 and divide it by any number. That isn't an issue, right? It's always defined. 0 divided by anything is 0. Anything divided by 0, that's undefined. So we never have to worry about the numerator for non-permissible values. We simply have to look at the denominator. So the numerator can be anything we want. That's never going to cause us any difficulties. It's just the denominator that has to be restricted. All right, let's try another one. What value of x would make that denominator equal to 0? What are the chances? Skylar, say that again. 2.5? Everybody agree with that? I don't. Shirley? Yeah, it's going to be the opposite side. So you take 2x plus 5 and you say, when is that equal to 0? Okay, solve for x. So you move the 5 to the other side. Then you divide by 2. So we'd say x cannot be equal to negative 5 over 2 or negative 2.5. Right? So you've got to be careful. Does this remind you of anything? Justin?
Radical expressions find the non-permissible values.
Yeah, that's part of it. But actually finding the value for x is an awful lot like solving quadratics. Right? Remember we have quadratics right down to 2 factors, and then we decided what would make each of those factors equal to 0? This is the same kind of work. Right? So you set it equal to 0 and solve for x if you can't do it in your head, and that's absolutely fine. All right, let's try another one. Ian, you have a note for me, by the way? So you're just walking in this late because... Were you? Oh, I didn't notice. Did you? I'm sorry, I missed that. I must be more observant. My apologies. You guys were so fast, it was a blur. Okay, anybody got it? Yeah? Negative 2. So, you're already thinking no?
Yeah, because then negative 2 squared is...
So negative 2 is not going to be a problem. Yep?
It'd be like undefined because isn't just x not equal to square root of negative 4?
So if you want to figure out, you would take this and you would set it equal to 0. And then you get x squared equals negative 4. And we know that that's not possible. So that means that there's no value for x for which this will ever be equal to 0. Right? Because if you take any value for x and square it, you're going to get a positive number. And when you add 4 to a positive number, it's certainly not going to equal 0. So will never be equal to 0. Therefore, we say the expression is defined for all values of x. Okay? So there are no restrictions, there are no non-permissible values for this particular expression, because there's no values that will ever make that denominator equal to 0. So many times you'll have non-permissible values, but not all times will you. So you have to be able to define and figure out when those two scenarios occur. Okay, one last one. State for me the non-permissible values for that one. Anybody have an answer for me? Dylan? Anything else? Anything else? You got half of them. There's another one. Say that again? Absolutely. Because we want to know when is x squared plus 7x plus 12 equal to 0. Well, what is that? It's a quadratic equation. How do we solve quadratic equations? We factor
Can I get Evie?
Having a problem? Okay. You're welcome. All right, where was I? Okay, so x plus 3 times x plus 4 equals 0. So that means if we solve this for x equals -3 and -4. So those are your non-permissible values. So if you have a trinomial in the denominator, you set it equal to 0, you now have a quadratic equation. And you solve the quadratic equation as you would have in chapter 3. See how everything keeps coming back? Just keep doing it over and over in different ways. All right. So if I had a fraction, because remember rational expressions are just fractions. Let's say I had this fraction. And I said to simplify it or to reduce it to lowest terms, what would you do? Tell me what you would do. Don't tell me what the answer is, but tell me how you would get to the answer. If I asked you to simplify or reduce to lowest terms, that's the way we're most familiar with it. That fraction, what would you do? Okay, this is grade 6 math. Tell me you know how to do grade 6 math. I know you do. Very quiet today. Yes? Okay, but you didn't tell me how to do it. You just told me the answer. I don't want to know the answer. I want to know how you're going to get the answer. Process, yes.
Divide the top and bottom of each bracket.
Okay, and why did you pick 5?
Because it's the greatest common.
Beautiful. So we divide top and bottom by the greatest common factor to get our answer in lowest terms. All right, so we're going to do the same thing. So to simplify rational expressions, you want to divide the numerator and denominator by their greatest common factor. All right, so let's start with an easy example. We'll do a monomial numerator and denominator. So 12x squared y cubed over 4x y to the 4th. So if I was going to reduce this or simplify it, I would look at each piece of it with like terms. So I'd first reduce the numeric part. So what would that reduce down to? Twelve over 4 reduces down to 3 over 1, because we would divide top and bottom by the common factor of 4. Then we go to the x piece. We've done this. We learned to do this in grade 9. X squared divided by x would become x over 1, yeah. And then y cubed divided by y to the 4th. How does that reduce down? What are we going to divide out of top and bottom? What's the biggest common factor of y cubed and y to the 4th?
Y cubed.
Y cubed. So y cubed divided by y cubed on the top will leave us with 1. And y to the 4th divided by y cubed will leave us with y. So our final answer would be 3x over y. Right? We've done that before. So sometimes you'll see people just divide it out and do it this way, right? And write the common factors above, and that's fine too. Whatever you do, whatever works for you. Whoops, lost the last piece. All right. Now, because this is a rational expression, we always have to, with our answer, give the non-permissible values. So what would the non-permissible values be? Hannah?
Why?
Is that it? Dustin?
X may not equal 0.
Okay, so you didn't sound super sure. You are correct. So here it brings up a really important point. You must find and state the non-permissible values before you simplify, right? If we don't restrict x from being 0, then we would end up dividing by 0 here, and we can't allow that. So if we wait till after we simplify it, the x disappears in the denominator, and we think, oh, no issue, there's no x. But there was at the beginning. So these restrictions apply to what we started with. All right? So this is a really important point. Always find and state the NPVs before you simplify. Otherwise, you may lose 1 or 2, depending. Okay? All right, let's look at another one. Now, we want to divide out common factors. Is the top factored? Is the top in factored form? No. So we can't divide out factors unless we have factors. And we don't have factors unless we rewrite the polynomial in factored form. So let's factor the top. How would we do that? Sorry, Lyndon? Not to factor it. Don't need it equal to 0. That would be if I'm solving it, not solving it. Ian? Anything else? Can I take out? I want to take out the GCF, right? That's right. So I'm going to take out the 2x, and I'm going to be left with x plus 4 over 4x. Now that it's in factored form, now I can look for factors that are common. So I would look at this and say, okay, I can divide out my x's, and I can divide out that 1, and that's it. There's nothing else I can divide out. Okay? So I'm left with x plus 4 on the top, 2 on the bottom, and what would my non-permissible values be? Justin?
X may not equal 0.
Correct. All right, x cannot equal 0. So I'm going to write down the steps for you, and then we're going to practice. Now, these are going to be the first steps of any work that we do in this whole chapter. And you're going to add to this as we go along, as you figure out what other steps you need to do depending on what the question is. So first thing is factor the numerator and denominator if possible. And I state if possible because sometimes it'll be in factored form. For example, 4x is in factored form. Because what does factored form look like? How do you know if something's factored? When something's factored, it's written as what? Yep? No, that's reduced to lowest terms. How do you know if something is factored or in factored form? Justin?
When there are no common factors between the terms.
No, that's lowest terms. Not answering my question. The same thing Skylar said. How do you know when something is in factored form? Okay. There's a little side. Don't need to necessarily write this down. Is 24 factored? Is that written in factored form? So write it to me in factored form. Are 4 and 6 factors of 24? That's written in factored form. If we want to do prime factorization, we'd keep going. Right? Now this is written in factored form. So if I had, say, something like 24 over 30, and I want to divide out common factors, what I'm really doing is thinking this is 4 times 6 over 5 times 6, and I'm dividing the 6's out. That's how I'm dividing, that's how I'm reducing with numbers. I just don't think of it, I don't actually write it out, but that's what I'm thinking in my head. What's the biggest number I can divide out of 24 and 30? So that's in factored form. Anything that is written as a product of factors is in factored form. So if we go back up to this question up here, 4 times x, it's written as factors already. That's how we write a coefficient and a variable, right? But this isn't being multiplied together. This is being added together. So if you have two terms and they're separated by addition, then they're not in factored form. If you have two terms and they're divided, or they're connected with multiplication, which this means 2x times x plus 4, then it's written in factored form. Right? Is he okay?
Yeah.
Okay, good. So now it's factored. So do you see the difference? Factored form means it's being multiplied against something else. And if it's not written in that form, then it's not factored, and then you need to factor it. Okay? Yes, Justin?
What about something like x plus 7?
That can't be factored. So x plus 7 is the factor. So that would be like 3. 3 can't be broken down anymore. So think of it kind of almost like a prime number. If it's x plus 7, which can't be factored, then x plus 7 is the factor that would need to be in common with something else in order for it to be reduced. Okay? It'll make more sense, I think, as we go through some more examples. All right, number 2. Once it's in factored form, then you're going to look for non-permissible values. Step 3, divide out all common factors from numerator and denominator. And finally, write your answer with non-permissible values, NPVs. So those are the 4 steps. And we'll be doing that, as I said, as part of every question that we do this chapter. So let's practice that. So following those steps, see if you can simplify. Sorry. Forgot to turn my sound off. So see if you can simplify that. So first we factor. So x plus 4, x plus 5, over x plus 4, x minus 3. Okay? So now we have these binomials that are being multiplied together. So it's in factored form. And x plus 4 is a factor. X plus 5 is another factor. So we're looking for factors that are commons. Because remember, x plus 4 is just a number, right? Let's say x was 3. Then x plus 4 would be 7, and x plus 5 would be 8. So the top would be 7 times 8. And the bottom would be 7 times, oh, I picked a bad choice, 0. I picked a non-permissible value. But you get the idea that those factors are really just numbers. Because if we knew what x was, then we could convert those to numbers. All right, so let's do non-permissible values. What can x not be equal to? What are the non-permissible values? Okay?
-4 and 3.
Beautiful. -4 and 3. And now I'm going to divide out the common factor, which is x plus 4. And then I'm left with x plus 5 over x minus 3. That's it. Okay? All right, let's try another one. So negative 12x squared minus 8x over 9x squared plus 12x plus 4. So again, we want to simplify that. So in the top, how are we going to factor that?
Take the 4x out.
Okay, exactly. I'm going to take the negative 4 out. Good. And that's going to leave me with 3x plus 2. Now, what kind of trinomial do we have in the denominator? Hopefully we're starting to recognize these now. First and last numbers are perfect square, so it's a perfect square trinomial, which means that both factors are the same. And to do that, we take the square root of the first term, we take the sine of the middle term, we take the square root of the last term, and then we double check. 3x times 2 is 6x, doubled is 12x, so we know that we factored it correctly. All right, non-permissible values. What's our non-permissible value in this case? Negative 2/3. Good. And now we divide our common factors out and we write what's left as our answer. Done. So far, so good? Okay. We're going to do a couple more. This is crucial. If we get this, to the rest of the chapter will go fine. Except maybe until we get to the word problems. All right, try that one. All right, so we factor this, and we get x minus 8, x plus 5. We factor the bottom, which is a difference of squares, and we get 5 plus x, 5 minus x. Now, very important that you write it as 5 plus x and not x plus 5. Well, actually, that one it doesn't matter, but the second one it does. You can't just reverse the order because you're more comfortable or used to having the x squared at the beginning. Because x squared minus 25 is not the same. So you have to, if x squared is at the end, then the x's go at the end. All right? So that's important. We're going to talk about that more in just a sec. What are my non-permissible values? Dustin?
X cannot equal 5 or -5.
Right, so we can just write that as plus or minus 5, as we've done in the past. We don't have to write them separately. And now, is 5 plus x and x plus 5 the same? Is that the same number, even though the order is different? Yes, because we're adding those two numbers, right? So let's say x was 3, 5 plus 3 and 3 plus 5 have the same value. So we can divide those factors out because they are the same. And we're left with x minus 8 over 5 minus x. All right? If it was x minus 5 and 5 minus x, would those be the same? No. How would they be different, though? Let's say if x equals 3, then we'd have 3 minus 5 and 5 minus 3. This would be negative 2, and this would be 2. So they will always be opposites of each other. The same number with the other sign. Doesn't matter what value you put in for x. Can you see that you're always going to get opposite values? One positive, one negative. So keep that in mind while you try this last one. Oops. All right, so we're going to factor this. 2x and x. I know I want to make 15, and I want a difference of 1. So if I look at my outside products, that's 30. So I can make 30 with 6 and 5. And because I want the difference to be negative, so I'm going to put a 3 there because that'll give me 6. So I need that to be negative and that to be positive. And then on the bottom, 3 plus x, 3 minus x. So we can do our non-permissible values, plus or minus 3. And here we have to be really careful. All right? We can't just take x minus 3 and 3 minus x and divide them out because they're not the same. But they're very close to the same. So we can do it a couple of ways. We could factor out of this a negative 1, which would make that negative x plus 3. So is negative x plus 3, is that the same as 3 minus x? That's the same, right? Because as long as the sign in front of the term is the same, then the value of that whole expression will be the same. So if I do that, then I can now divide out the 3 minus x's. But I can't forget that I have this extra negative 1 factor in there. So what I'm going to do is I'm going to multiply it in to the numerator. So my final answer would be negative 2x minus 5 over 3 plus x, where x is not equal to plus or minus 3. So we always like to keep our denominator positive. We've talked about that before. So we are always going to put that negative factor into the numerator. All right? Now another way to think of it is this. If I have 2x plus 5 and x minus 3, if you remember that those will always give you opposites, then when you divide them out, you're going to be left with a factor of negative 1. Right? If I had negative 8 over 8, and I was going to reduce that down, I would divide top and bottom by 8, and I'd be left with negative 1 on the top. So you can think of it that way if it makes it clearer to you. And then that negative 1, of course, gets multiplied into the other numerator, just like it did in the first way that I did it. So either way, it doesn't matter to me. Just make sure that you change the signs of the terms that are last on the top in the numerator. Okay, that's it. Now we just need to practice and get better at it. So again, if you need help after school with some factoring, come and see me.